Okay, so we're going to do a problem today with electric fields, and this will be a problem that mixes information that we learned first term about forces and mechanics together with our thinking about electric fields. So let's imagine that you have a small ball, not unlike the pith balls that we've been doing demonstrations with. It's suspended by a thread in a uniform horizontal electric field that has some magnitude E that is currently unknown. The ball has some specified charge, minus 3.1 microcoulombs, and it's displaced by some angle, 10.5 degrees, from the vertical. And what we want to do is we want to use that information to find out what is the magnitude of the electric field vector. From a very practical viewpoint, this is the way that you could find out the magnitude of any electric field if you had the ability to understand the properties of some charged sphere that you had access to. Okay, so this is a problem involving forces, and so the very first thing that I think is useful always to do with problems is to draw a picture of the physical setup. Now there's always more than one way to do the problem, and there's always more than one way to start the problem, and in particular with problems like this, as with many of the physics problems you've encountered, there are lots of implied bits of information that you need to key off of and in fact use if you're going to actually solve the problem, and this problem certainly is no different. There's a lot of different bits of implied information, and you can start with some of them or you can start with others of them. You'll set up the problem a little differently depending on the choices you make, but in the end I claim you'll get the right answer. Okay, so for instance, as an example of what those choices are, I can either start from the information I'm told about the charge, that it's hanging with a certain angle away from vertical, or I could start with something that I'm told about the electric field, namely that it's a uniform electric field, which has implications about how we make that field based on the sorts of things that we've been talking about in class. Let me go ahead. For me personally, I think it's more natural to start from the thread. So let me start with imagining what the thread looks like. So the thread is hanging from something, a hook on the ceiling or something, and it is displaced from the vertical. Okay, so I'm going to draw it shifting off to the left there by some angle. Okay, let me label that angle theta. We're told in the problem that that angle is 10.5 degrees. Okay, so I've arbitrarily made a choice here. I've chosen that displacement angle to be towards the left. And because I'm told the sign of the charge, it's negative, it tells me something about the electric field. I've made a choice that tells me what the geometry of the electric field in this problem is going to be. It doesn't matter what that choice was. I could have just as easily chosen that that charge be displaced to the right, and that would have had a different implication for the electric field, but it doesn't change the nature of the problem. Okay, I would have been fine either way. Okay, so I know that positive charges feel forces in the direction that the electric field points, which means negative charges feel forces in the direction opposite the direction that the electric field points. Since the electric field is uniform, it's going to point in the perfectly horizontal direction here, and given the displacement from vertical, that means that negative charge feels a force pointing to the left, which means my electric field must be pointing to the right. Okay? Now, I could have started this problem by choosing the direction of the electric field and then worked out the implication for the direction that the thread is hanging. It's fine either way. Okay? So, that's the physical picture. There are other accoutrements you could put in the picture. You could put parallel plates in and assign charges to the plates to set up your electric field. That's all kind of extraneous and not important to the problem. But if it helps you to imagine, to visualize the problem, then those are perfectly good things to do. Okay, so now that I have my physical diagram, the next thing I need in order to solve the problem is actually the free body diagram. So let me draw that. I'll represent the ball by a dot. There are three forces in this problem. So the most obvious one is the tension of the string on the ball. There is the weight of the earth attracting the mass of the ball. And then there is the electric force that's causing the displacement away from vertical. So that's the electric force on the ball. Okay? Now, this problem is a problem in statics. The ball is not moving, nor is it accelerating. So Newton's second law tells me that if it's not accelerating, if the acceleration is zero, then the sum of all the forces must be zero. Okay, and that's the key to solving that problem. What this tells me is that if I look at all the components of the forces in both the x direction and the y direction, that all of those components must indeed solve to zero. Okay, so let's go ahead and break that problem up into components. Okay, so let's start with the tension, because the weight that the ball feels in its attraction to the earth is purely in the vertical direction, so that's going to be easy. And the electric force that's felt by the ball from the uniform horizontal electric field is purely in the x direction, so that'll be easy. So the complicated bit of this problem is actually here, the tension force. Okay, so let me add to the free body diagram the angle of interest. So this is the angle theta, which is the same angle that we see up there. So I can write both the x and the y components of the tension. So the x component of the tension is the tension that the rope places on the ball times, given the geometry of this angle, you have to be careful, the x component is given by this times the sine of theta, and the y component, Ty, is again given by the tension that the rope exerts on the ball times the cosine of the angle. Okay, now I'll use both of those expressions here as I do the two components. Newton's second law works equally well in a component fashion as it does in this kind of summation fashion we wrote here. So in the x direction, the horizontal direction, I know that the sum of all the forces in the x direction must equal 0 because the particle is not accelerating in the x direction. And so the sum of all the forces in the x direction are the x component of the tension minus the electric force on the ball. Okay, and the minus sign tells me that they're pointing in opposite directions. So I'm going to write that as the force of the electric field on the ball. Those must sum to 0. And so that implies that the tension in the x direction must equal the electric force on the ball. Now I have expressions for both Tx and the electric force on the ball. Tx is given up here in terms of an unknown thing, in terms of the tension. So let me write that. That is the tension the rope exerts on the ball times the sine of theta. And then the electric force felt by the ball is a function of the strength of the electric field, the thing that we're looking for, times the amount of charge that's carried on the ball. Okay, so in this case, I'm going to write the force due to the electric field as Q times E. Okay, now the way I've set up this problem and the way I'm doing this problem here, you have to be just a little bit careful because all of the signs here are getting used in order to tell us something about the directions of the force. And in this case, I've used the fact already that the charge is negative to tell me which direction that should be displaced. And so when I get to the end of the problem here and I put in numerical values, I need to make sure that I don't use that sign again. I've already used that sign to give me the sign that I've used right here in this equation. So you just kind of got to be careful. If you're worried about making a mistake like that, okay, I know I've used the charge here, and so what I'm going to do right here to make sure I don't forget is I'm going to put absolute values around that charge, and that'll help me remember later. Okay, so let me just leave that alone for a minute. Let me now go on to the y direction. Okay, and just as in the x direction, the sum of the forces in the y better equal to 0. And just as in the x direction, I have the tension in the y direction minus the weight that the earth exerts on the ball. Those must sum to 0, which again implies that Ty is equal to the weight that the Earth pulls on the ball. Okay? Now, just as above, I have to be careful. I've used the fact that the Earth is pulling downward, not vertical, to assign that sign. So when I put in an expression for the weight here, okay, so the weight is given by mass times the acceleration due to gravity. When I put in a value for gravity, I can use 9.81 meters per second, not negative 9.81 meters per second. I've already used that minus sign to imply that the force is in the opposite direction from the tension. Okay, so that's the weight force, and then again I have an expression for the tension that I worked up here. So this is the tension that the rope exerts on the ball times the cosine of theta. Okay, so what I'm after is the electric field. Okay, so let me solve this equation for the electric field. You'll see it'll give me some expression in terms of Q, which I know, some expression in terms of theta, which I know, and some expression of the tension in the rope, which I don't know. But if I go to the x direction, as is often the case, we get a piece of information we know. I know the acceleration due to gravity. I'm told the mass of the ball. I know the angle, and so I can solve this expression for the tension. Okay, so the tension of the rope on the ball is equal to the mass times the acceleration due to gravity divided by the cosine of theta. And the electric field is equal to the tension of the rope on the ball, whatever it might be, times the sine of theta divided by the absolute value of the charge. I can take this expression for the tension of the rope on the ball. I can substitute it in there for the T. And so this gives me mg over the absolute value of Q times sine of theta divided by cosine of theta. And that is the tangent of theta. Okay? So, I know the mass. The mass in the problem is 0.025 kilograms. Acceleration due to gravity is 9.81 meters per second. The charge is 3.1 times 10 to the minus 6 coulombs. And the angle is 10 degrees. Okay, I'm running out of space here, so I'm not going to write those numbers out on the pad, but you can insert them, carry the units with you. And if you punch those into your calculator, you will find that the electric field is 1.4 times 10 to the 4 newtons per coulomb. Okay? So make sure you carry along your units to ensure that you do indeed get units of newtons per coulomb. But m times g is a force, that's newtons. The units of charge are coulombs, and there are no units with the tangent. Okay? So this is our answer to this problem. Okay? Like I said, there are a variety of ways to do this problem. You can come at it in many different directions, but I claim you will always get to the same answer no matter how you do it. Okay? So good luck doing some problems like this. We'll do a couple more examples, and I'll see you next time.